Hello, everybody, and welcome back. We have now the second round of the, I would say, UK morning talks and Europe morning talks, I would say. But now I know it's afternoon in Iran and in China, probably closer to evening. And still people in North America, they still are in the bed. So, but anyhow, whenever you are, we welcome you back. We have Karim Barigu and also Said Safarwaisi, two of Yandon's students, one former student who has turned to a very, very active researcher now. Karim, actually, a proud proudly co-authoring a paper with him, and I think he has a very brilliant mind and has a very brilliant future, very active in many areas in actuarial science. He's now doing, I think, a postdoc in Lyon University. Is that correct? And today we have him as one of our speakers. Thank you very much to accept my invitation. By the way, Karim, he has worked a lot on valuation, market consistent valuation. And I have to say that I was external examiner of his dissertation, and I know the quality of his work. So that is why I'm very happy to have him. So today he's going to talk about pricing equity-linked life insurance contracts with multiple risk factor by neural network. So Karim, you have 50 minutes and few minutes for questions. Thank you very much.
Thank you very much, Irbad, for the kind introduction. And thank you very much for the invitation. That's a great pleasure to present this paper. Before talking about the paper, unfortunately, the presentation is online, but that's a pleasure for me to present to Iranian audience. And it's not the first time, because I would like to mention that I will present full. I would like to mention that in 2017, we organized a workshop at the Insurance Research Center in Tehran. It was organized by my supervisor, Professor Yandan, myself, Hamzan Bali, my PhD colleague at that time, and Dr. Ahmad Salanejad. So we had a very nice time to, it was a 2-day workshop where we discussed for evaluation of insurance liabilities. Here you can see me with my with the head of the Insurance Research Center, Yandan and Hamza Bali, and you can recognize with the picture that it was taken in Iran.
Yes, exactly.
And here it's another picture with the participants. I think it was taken on the last day, and it was a very wonderful event. After that, I visited Iran, so I went to Ardabil, Tabriz. That was a wonderful experience, and I hope that after the pandemic, I will have the occasion to go back to Iran.
Yes, of course. We are looking forward into it.
Yeah. So today I will present a joint paper, a joint work with Lucas Delong, who is a professor at Warsaw School of Economics. The paper is entitled Pricing Equity-Linked Life Insurance Contract with Multiple Risk Factors by Neural Networks. So here is the summary of the talk. So I will first introduce the general concept of valuation and fair valuation in insurance. Then I will in fact present the setting, because we will work with financial and insurance risk. So I will define the different types of risk. Then the main part of the talk will be about the pricing itself. So in fact, I call pricing, but you can see it as the valuation, let's say, the fair valuation of equity linked. Then I will show how to derive, in fact, the partial differential equation for the pricing, and how we can solve this PDE with neural networks. And then I will go through some numerical results to discuss especially the sensitivity of the price with the different parameters, and then I will conclude. So we'll start from the basics. So essentially, in insurance, you have two parties, the insurer and the policyholder. The policyholder transfers risk, so in fact, an insurance liability to the insurer, and the insurer has, in fact, to determine usually premium for the policyholder. But in this talk, we'll more generally talk about the value. What is the value of a certain insurance liability S? What is the fair value? And in fact, in this talk, I will more focus on life insurance, even though you can also compute market consistent valuation, fair value for non-life, but these are quite different type of risk. So in this talk, I will focus on life insurance. So in fact, this problem is quite complicated because an insurance liability depends on several types of risk with different natures. So on the one hand, you have financial risk. You have the interest rate, the equity, the volatility. These are financial risk. And on the other hand, the insurance liability also depends on what we usually call actual risk or biometric risk. These are the mortality risk. This was also mentioned by Herbot yesterday. You have some systematic and unsystematic mortality risk. So I will come back to that. But essentially, in this mortality risk, there are some risks that you can diversify by increasing your portfolio. And there is some risk, like the longevity risk, that you cannot diversify. So it's well known that we are all living longer. And this type of risk, even though you increase the size of your portfolio, you cannot eliminate this risk. So you have to find a solution for that. So essentially, in the literature, you can find two types of valuation. So the first type of valuation, I would call it the traditional actuarial valuation, which is based on the principle of diversification. So for instance, let's say that you have a survival benefit in 10 years. So if you are still alive in 10 years, you receive a given amount. Well, this type of, this is simple life insurance. And the idea is that if you have a large portfolio, by the law of large number, you should converge to, on average, to the expectation. Of course, so you have the expectation, and then, of course, there are some risks that you cannot diversify. And so therefore, we add a risk margin on top of the expectation. That's the valuation that you can that you find here. And an important characteristic of this type of valuation is that the valuation is performed under the real-world measure P. So it means that, for instance, you have historic life tables. So this is what really happens is under P, and you determine the valuation based under the real-world measure. On the other hand, in finance, you have another type of valuation, what I call here financial valuation or risk-neutral valuation, which is based on the principle of no arbitrage. So it tells you that if there is no arbitrage in the market, the value of a certain liability or claim or derivative, let's say S, can be expressed as an expectation or a risk-neutral measure Q. And the set of feasible Q measure can be followed from observed market prices. The difficulty with to apply this in insurance is, in fact, that in insurance you are not in a complete market. In fact, if you are in a complete market, there is a unique Q. But in insurance, we are in incomplete market. So there are, in fact, an infinite choice of measures Q. And this Q will, in fact, reflect the risk averseness of the investor. So because in insurance liability, you have a combination of actuarial and financial risk, you cannot use, in fact, one valuation or the other, but you should find a way to, in some sense, combine the two approaches. In fact, that was the focus of my PhD. So insurance liability are only partially hedgeable, not fully hedgeable. And therefore, in fact, in the literature, often a two-step approach is considered. So a first one, which is called hedge-based valuation, or here I mentioned as a two-step hedge-based approach, is coming from the paper of Dan et al. 2017 that I co-authored. And essentially, the idea is to split the claim into two parts. First, you hedge one part of the risk. That's the V theta zero. So that's your replicating portfolio. That's the hedgeable part that you can, for instance, determine via some hedging techniques like quadratic hedging. And then Of course, this is not sufficient. There is some residual risk. And then for the residual risk, which is denoted here S minus V theta t, you apply another principle, what we call here an actual principle on the residual part. That's one idea that we have proposed in this paper. Another type of valuation that is considered in the literature is the two-step valuation or the two-step conditional approach from Purcell and Statute 2014, where essentially there the idea is not to find a sum, but to find a conditional argument. So let's say that we have a claim S, and here Y denotes the vector of asset prices. So the idea is to first condition on the asset prices. That's the inner step. So because you condition on asset prices, you have in fact a financial derivative. And because you have a financial derivative, you can use a financial valuation as the outer step. And this gives you the two-step valuation. So that's a different approach, but both approaches are considered in the literature. In fact, if you are new to the literature, I will give a brief overview. In fact, this research on fair valuation, market consistent valuation is growing rapidly in the recent years. I would like to mention some co-authors and some other researchers. For instance, the valuation that I just mentioned from Dan et al. 2017 was generalized in a discrete multiple setting by myself and co-author 2 years ago, and in continuous time by DeLong et al. Irbot Assa and his co-author Cospo Dinov also worked on market consistent valuation. In fact, in imperfect markets, that's an important issue because, as I mentioned here, the financial valuation here is linear because you have an expectation. But if the market is imperfect, the valuation is not necessarily linear. And therefore, the author consider two types of market consistency, market consistent valuation, type 1 and type 2, and discuss this issue. Also, the two-step conditional valuation that I mentioned from Purcell and Statute, Ahmad Salanejad also worked during his PhD on that. So you can find, he also applied that to pension contracts. So you can have a look at this paper. Other authors consider not a two-step, but a three-step valuation, where essentially the idea is to split the liability into 3 parts. You have a first hedgeable part, which is related to finance. Then you have a diversifiable part that I mentioned, and then there is a residual risk. And they apply a different type of valuation for each type of risk. And it was also generalized by Linders 2021. And then finally, I would like also to mention that here I mentioned that you can determine the hedgeable part by quadratic hedging, but you can also use some other asymmetric function to determine your hedging portfolio. And if you are interested in that, I worked on that last year in another paper, but also Chen et al. Consider what we call convex hedging, convex hedgers, where you can consider convex function for your hedging to determine your hedging portfolio. So that's so you can find all the reference at the end of this presentation. So the aim of this paper is threefold. First of all, we would like to price equity-linked contracts in a general incomplete markets with different types of risk factors, so stochastic interest rate, equity, stochastic volatility, and stochastic mortality. So we want to determine what is the pricing PD. I guess that if you are familiar in finance, you know the Black-Scholes PD. In some sense, this paper is a broad generalization of the Black-Scholes PD in insurance. Secondly, we would like also that there is now a new stream of research about solving PD with deep learning. And in fact, that's also something that we want to present in this paper, is how to solve relatively complex PDEs using neural networks. That's the second part of the paper. And at the end, we will also discuss some sensitivity analysis to model parameters, and also compare our approach with Monte Carlo approach. So the model for financial and insurance risk. So first of all, what is equity-linked insurance? So I don't know if you are familiar, but as the name indicates, it's an insurance which is equity-linked. So it means that the death and survival benefits are linked to an investment portfolio. So instead, for instance, instead of receiving, let's say, 1,000 if you survive in 10 years, well, you will invest in a portfolio of bonds and equities, and you will have a survivor guarantee, insurance guarantee, in case of survival at the end of the contract. You can also have this. So the idea is that in exchange of a fee, the insurer offers a financial protection for the market downturn in case of death or survival. So you are then, so in some sense, you pay a constant fee on your investment portfolio, but in exchange, your loss is in fact limited. So the main research question, therefore, is, well, we have this contract. What is at any time, from time 0 until the maturity, what is the value of the insurance liability towards the policyholders? That's in fact an important question because, well, in solvency, insurance solvency regulations, you have to compute a solvency capital requirement. And for that, you need, in fact, to determine the fair value of your liabilities today and 1 year from now. But that's important to determine what is the value at any point in time. So that's the main question of this paper. So how do we model the financial markets? Of course, the standard Black-Scholes financial market is too restrictive because you assume constant interest rate and volatility. And especially in insurance, when you have long-term liabilities of 20, 40 years, you have to consider a more realistic setting. So what we consider here are some popular models for each type of risk. So for the interest rate, we consider two-factor interest rate model. So here RT is the interest rate. So psi-t is a deterministic function, and you have two stochastic factor X and Y that drive the interest rate. So that's a common use model. And then for the volatility, we use the well-known Eston model, Eston stochastic volatility model. So ST here is your equity, which follows a kind of Black-Scholes dynamic. But here, the main difference with Black-Scholes is that you have VT, which is your volatility, which is itself stochastic. So an important remark here is that, well, we cannot work under Q because, well, if we work under Q, well, we don't know under which Q we have to price because the Q is not unique. So because the market is incomplete, we work under the physical measure P for hedging purposes, and we will find a way to determine what is the hedging portfolio. But then that's important to work under the real-world measure P. So we don't pick a specific Q measure. So how does it work for the policy order? Well, the policy order starts with an initial premium here denoted by F0, and this initial premium is invested in bonds and equity with a certain percentage. The percentage here is denoted by U. So in the first line, you have the dynamic. So here F is the dynamic of the account of the policy order. So the first line is the bond dynamic. So as we just mentioned, the second line is the equity dynamic. And as I've mentioned, because there will be some insurance death and survival benefits from this account dynamics, there is a constant fee denoted by C here, which is withdrawn from the policyholder's account, a constant fee. And in exchange of this fee, the insurance contract includes some death and survival benefits that are denoted here. So FT is the fund at time t. And then we see that it's protected with a certain level D star and S star. So it means that if you die at a certain time t, you are guaranteed to receive at least D star, and at the end you are sure to receive at least S star. So that's the insurance guarantees of the contract. Okay. also now we have also to define what is the dynamic for the force of mortality. Of course, it is important to take into account systematic and unsystematic mortality risk. For that, in the literature, what is usually considered is to consider, for instance, a Poisson process where the intensity is stochastic. So that's important because the stochastic intensity will take into account the systematic risk. That's an important factor. So here we assume that the lambda, the intensity, is stochastic and follows this dynamic. So we follow the approach of Luciano et al. 2008. And here we just introduce two processes. So NT here are in fact the number of dead people at time t, and JT are the number of still alive people, so enforced policy at time t. So of course, both are complementary. The sum of the two equals the number of policy orders n. All right. So now this was about the risk factors. So now how do we price equity linked in continuous time? Well, in fact, there are four main steps. Well, first of all, because we're in complete market, we have to first set up a hedging portfolio. How do we set up this hedging portfolio? In fact, let us say that we have liabilities. We want to find a portfolio of assets that is as close as possible to your liabilities. So therefore, in continuous time, what we mean is that we want to determine a hedging portfolio that minimizes the quadratic variation of the net asset value process, which is itself the difference between assets and liabilities. So it means that in some sense, you want to find a portfolio of assets which is as close as possible to your liabilities in the quadratic sense. That's the first part. Of course, because you cannot fully hedge your portfolio, there will be some residual risk. And for this residual risk, what we propose is to apply standard deviation risk margin. So it means that there is some residual risk, and we apply an actual principle for this residual risk. That's the two-step. And then, in fact, we work in continuous time. So what we get at the end is, in fact, a PDE. In fact, a quite complex PDE. It will be, in fact, a system of nonlinear PDEs. And then that will be the third step. And then finally, we'll show the connection between partial differential equation, PDE, with FSDE, which stands for forward stochastic differential equation, to solve the problem using neural networks. And so, in fact, I will mention that later, but it's in fact a generalization of the approach of Han et al. So if you are interested in solving PDEs using deep learning, I highly recommend you to have a look at the paper of Han et al. So before we have given the dynamic for the policy orders accounts, but here now we look at the aggregate portfolio. That's the portfolio of the insurer. So in fact, the insurer will aggregate all the contribution of the policy order into a hedging portfolio, and the aim of the insurer is to optimally match the liability. So here you see the dynamic of the hedging portfolio. So again, the first line here is the bond dynamic. The second line is the equity dynamic. And then the third line is the fact that what is not invested in bonds and equity is invested in cash. That's the third line. Then you also have the fact that policy orders pay a certain fee C. So for the number of people who are still in the contract, they pay a constant fee C. So that's the fourth term. And then finally, of course, when some people die in the portfolio, you have to give the insurance death guarantee, D. That's the last term. That's the full dynamic of the portfolio. And of course, the initial portfolio is n times the initial premium, right? So what we want now is to determine what is the θ1 and θ2. Of course, the survivor benefits. So here, JT, SFT are the survivor benefits at the end. Of course, this does not affect the dynamic of the hedging portfolio. That's only at the end. So the next two slides will be a bit technical, but then it should be okay. So here, of course, we want to introduce the general approach. So here we have, in fact, all the risk factors, because we have a lot of risk factors. We just put all the risk factor into a vector Z, which includes X and Y, the interest rate, F, the fund, V, the volatility, and lambda, the mortality. So that's 5 risk factors. And also you have to, and then we introduce XT, which is the net asset value process. That's an important process. That's the difference between your asset and liability. So your asset is your hedging portfolio, V theta T, and your liabilities are denoted here by phi. So here, phi T, you have to interpret it as the fair value of the liability at time T, given the risk factor ZT, right? And the JT is the number of policyholders that you have at time T. So in fact, to be exact, it depends on 6 risk factors. So you have Z, which contain 5 risk factors, and you have the number of policyholders, which is itself, of course, a risk factor. So it's a function of 6 random samples, right? Random factors. Sorry. So as I've mentioned, we proceed in 2 steps. First of all, we determine the hedging strategy theta that we mentioned before, which minimize, in fact, the local variance of the net asset value process. Of course, if you work in a Black-Scholes setting, in fact, it doesn't really make sense, because in complete market, you can completely minimize the local volatility. So you get a local volatility of 0. And in fact, there is no residual risk. That's the definition of a complete market. But here in an incomplete market, there is some residual risk. And for this residual local variance, in fact, we price it using a standard deviation principle, which is given here, right? So the overall picture is that first we determine a hedging portfolio, and then we use an actual principle on the residual risk. So here it's what we get at the end. So I will not go too much into the details, but that's the solution of the general problem. So in fact, here it's not one PD, it's a system of PDs. Because in fact, these PDs are connected, so they depend on K, which is the number of policyholders. And of course, if you have, so here the phi K TZ is the price at time T and factor Z, given that you have K policyholders, right? Of course, if you have K policyholder and someone dies, then you have a portfolio with K minus 1, right? So in fact, these PDs are connected with each other. And this, in fact, you can see this at the second line here. You have phi K minus 1 plus D minus phi K, K lambda. So it represents the fact that if someone dies, your portfolio, your PD, which was focusing on phi K, you have to pay a death because there is one person who died. So that's the DTF. And then you have a new portfolio of K minus 1 person, that's phi K minus 1. So here, this represents the death benefit. Of course, and then the third and fourth line, in fact, are the risk margin. So in fact, if there were no risk margin, there would be only the first 2 lines. But here it's to take into account that there is some residual risk. So you have to add a second, this term. And then, of course, finally, you have the final condition, the fact that at maturity, we'll have to pay S, the survival benefit, times the number of policyholder, which is K, right? So that's the general PDE. And now the second part of the presentation is how to solve this PDE using neural networks. So one specific case, in fact, if you consider this system, but in a Black-Scholes setting, in fact, this reduces to these most simple PDEs. In fact, the first line, if you are familiar with the Black-Scholes PD, that's exactly the Black-Scholes PD. And then the second line is, in fact, the risk margin. So you add a term to take into account that there is some risk due to the fact that you cannot completely hedge the insurance risk. And the alpha here are the risk margin, the standard deviation coefficient. So we see that as alpha increase, so here it's only survival benefit. So we see that as alpha increase, the lambda here, the adjusted lambda decrease, and that's what, and so if the lambda decrease, it means that you increase the survival probability. And that's what you would expect for risk margins. So if you have some guarantee at the end, then if you want to be safer, you increase the survival probability. And that's exactly what you get here at the second line. All right. So now I will go through the second part, which is, in fact, how to solve that using Ford's stochastic differential equation. That's a slide a bit technical, but I will explain more in detail. So in fact, if you are familiar with the literature on PDE, there is a close relationship between PDEs and FSDE. In fact, this FSDE can be represented as a FSDE as follows. So in fact, the fair value, let's say at time t, can be expressed as the fair value at time 0 plus some additional random factors. And in fact, that's an important point, because now, given that we have all these dynamic, we'll use that to implement our neural network. Because in fact, what we want at the end is to determine phi n0 z0, which is the price at time 0, given that you have n policy orders. And now the idea is that we will discretize, because here, of course, these are random factors. So you discretize these random factors using a Euler scheme. And then with the Euler scheme, you can go from time 0 to time t. So here's the dynamic for the FSDE. If you discretize, that's what you get. So here, that's the fair value at time tn plus 1. You can express it as the value at time tn plus different terms. Here, in fact, all these terms look complicated, but in fact, these are only the discretization of this term. You discretize and you get this term. So now, what is where do we need the neural networks is that when you go from time tn to time tn plus 1, all what is in black, you know it given time tn. But there are two unknown quantities. These are the quantities in yellow. You have, in fact, the gradient of your fair value, the gradient of phi here in yellow. This part you don't know. You know phi GTN, but you don't know the gradient of phi GTN. That's one thing that you don't know. And the second part here, the second unknown, are the fair value with one less policy order. So at time tn, you know phi GTN, but you don't know phi JTN minus 1. So that's something, this is where we use neural network to approximate these two quantities. So this is the essential part. We'll use neural network to approximate delta phi, delta phi and phi GTN minus 1. So now I would like to briefly mention what is a neural network for people who are not familiar. In fact, roughly speaking, a neural network is simply a quite complex nonlinear function. In fact, mathematically, you can define it as a composition of a affine transformation and activation function. The usual way to represent it is that you have some input and one output, and then you have several types of layers and neurons for the complexity of the neural network. The more layers and the more neurons you add, the more complex the function is. But why neural networks are often used is because, in fact, there are some theoretical theorem that tells you that you can approximate any type of function, but the general idea is that you can have a relatively complex function if you increase the neural networks. So usually you have you start from a general complex structure, and then you train your neural network, and you get the nonlinear relationship between input and output. Here, in our case, the input will be the risk factors, and the output will be exactly what we mentioned here, the delta phi and phi GTN minus 1. So as I mentioned, and in fact, this work on neural networks is inspired from, I will just check the time. Yeah. is inspired from another paper, Han et al. In fact, in Han et al, they only consider pricing, in fact, a single PDE. That they consider a single PDE, which is multidimensional, semilinear parabolic PDEs, and they show how to solve this using the approach that you mentioned in our paper. So here, and also the paper of Chen Wei Nam consider some different type of architecture. And what we propose in this paper is a generalization of this approach, in the sense that here we don't consider one PDE, but a system of PDEs. And because of that, it increased the complexity. In fact, only, instead of using one neural network, we'll need, in fact, two neural networks, one for the gradient and one for the jump component. That's the main contribution of our paper on that side. So, as I mentioned, we'll use neural network to approximate two functions that we don't know, which is which is the price gradient, that's the neural network 2, and also the function with one less policy order, this is the neural network N3. Also, I will mention that later, but in fact, for the price at time 0, we also use a neural network. Because in fact, you can say, well, the price at time 0 just an unknown quantity, but in fact, you can improve your neural network by including this as a neural network, in the sense that instead of determining one price with neural networks, you can also determine a surface of prices with different initial parameters, and that would be in this first neural network. So at the end, you get a complex structure with 3 neural networks here, N1, N2, and 3. Of course, you start from some initial conditions, so you can simulate your patterns and get, at the end, a final value at maturity. And then we use the deep learning, so the neural networks, to find the optimal parameters. So how we do that? So we use the Euler scheme that we presented here to go from time 0 to maturity. So you get some approximation here, phi hat. And what you know at the end is that you get the survival benefit, JSFTM. And now the optimal parameters are found by minimizing this difference. That's the key argument of the architecture. So here I just draw an illustration. So here, what you have here, you start from Z0 and G0. These are, for instance, constant numbers, initial parameters. At time T1, you can simulate your risk factors Z and J. So these are also random factors. So from your initial condition, you have 2 neural networks that I call here NN1 and NN2 that gives you phi 0 and delta phi 0. Then you can do the same at time 1. And then you can go forward in time from time 0 to time 1, from time 1 to time 2, and so on, to get a phi t, which depends, of course, on the neural network parameters. And to determine these parameters, then you minimize the terminal condition. And after some training, then you get the optimal parameters. That's the overall architecture. So now I will take the last 5-10 minutes to discuss the numerical results. So of course, what we are interested in this paper, even though we can determine the fair value at any time, here we focus on the fair value at time 0, given some initial parameters. So here we just took some parameters for illustration, like constant fee of 1%, D star, and so we start from a fund value of 1, a maturity of 1 year, so really simple, and D star and S star are guaranteed of 2%, right? And there are some, we assume that the X0 and Y0 are 0 at time 0, and some initial volatility and force of mortality. And more importantly, this is a portfolio of 100 policy orders. So here, that's what we get. So essentially, we train the neural network, And we see here the convergence for one price. So we see that, well, essentially there is a random initialization. So the price that starts from 0, and then it quickly converges to a certain. We see that after 100 epochs, it converges to a price of around 6. So there is a quite fast convergence. So here, if I remember, it takes for one price, it takes less than 1 minute, I think. And here we see that as the number of epochs increases, there is a decrease of the mean square error. And here we see that the mean square error decreases around until 0.5. 0.5, and this is in line with the literature. Also, the good thing with neural network is that you can have important computational efficiency, because you can determine not only one price, but a surface of price at the same time. Because let's say that you start from initial conditions. So here we start from initial parameters, and you can randomly sample the initial parameters and feed that into a neural network. In fact, the neural network will estimate the surface of price in one training. So that's a big advantage of neural network, is that you don't have to do the calculation for each price. You can determine plenty of price, like a surface of price at the same time. So here, for instance, what I did is that I started from my initial parameters, and then I randomly sampled with plus minus 25%. So I just randomized my initial parameters, and then I train my neural network. And this is what I get. So I see that, as you can see, after 100 epochs, so there are different initial parameters. So the price are going into different directions. But we see that after 100 epochs, there is a kind of stabilization of the different prices. And here we see also with the mean square error, there is a kind of fast convergence towards 0. So I also did some sensitivity to different parameters. So for instance, here we started from x0 and y0 equals 0, but if you, if we move the interest rate to 1%, we see that it has a quite important impact. There is like a minus 16% of price change with a 1% change. So also it's just 1 year reliability. So that's also why the interest rate has important effects. So we also changed the number of policy orders and the initial premium. We see that, of course, as the initial premium increase, there is a fast decrease of the price change, which is normal because if you remember, when the initial premium increase, here we don't change the guarantee. So of course the guarantee, the insurance guarantee are decreased. So that's explained why the price change decrease. And of course, as the number of policy order increase, we have an increase of the price. Here, we also change the initial force of mortality and volatility by plus minus 25%. So we see that the force of mortality does not really have an important impact, but the volatility has a quite important impact. So we see that if we make a plus minus 25% change of the initial volatility, there is more than 10% change of the insurance liability. Yeah, and then to finalize, I would like also to compare with another approach like Monte Carlo pricing. So let us say that we have a survival benefit, and we are in a Black-Scholes setting, a survival benefit with a certain payoff function, let's say S ft at maturity. In fact, there are two ways to solve this type of contract. Either you solve the PDEs that I mentioned earlier. You can solve this PDE using our neural networks. Or another approach is that, in fact, you can directly solve this by simulating by Monte Carlo pricing. So you just simulate random path, and then you just take the average. Normally, the two approaches should converge. And that's what you obtain. So here in the green line is the price that you obtain via Monte Carlo pricing. And here the red dots are the neural network price. So we see that only after 25 epochs, so it's just a matter of a few seconds, there is a fast conversion to the Monte Carlo price. And we have a relative difference of 0.2% only after 100 epochs. And here we see the pattern. The pattern is not really smooth for the MSO, but we still see that after that there is a fast decrease of the MSO as the number of epochs decrease. So to conclude, so here in this paper we presented we derived in fact a system of nonlinear PDEs for the fair valuation of equity-linked insurance in a general incomplete market. I think it was not obtained already in the past, so I think that's already a nice contribution. And also the second part is we show how we can solve this relatively complex system of PDEs using the connection with BSDs and neural networks. And I would say for future research, I think it's a very nice field, deep learning and neural network, because I think you can gain a lot of computational efficiency using neural network, because as I showed, you don't need to redo all the calculation, but you can have an estimate of a surface, and I think it can really decrease the computational burden. So thank you very much, and here are all the references.
Okay, Karim, thank you very much for wonderful talk. Actually, it was more beyond my expectation because the explanation was so good, and I learned a lot about this, and I think you explained everything with good details. Yes, thank you very much. So I'm waiting for people to ask questions, otherwise I can go ahead. Yes. Can you write it? Yes. Okay. It's coming. I have to take this out. Okay. Thank you for your speech and applicable study. In Iran, we have a sort of life insurance called investment-linked insurance, investment-linked life insurance, which might be a bit different from equity-linked life insurance, which you mentioned. In investment life, policyholder is benefited from the profit of his/her equity investment as well. Okay. I like to know if in your model this equation and calculation is considered or possible to be or not. Yeah, very good question.
Okay, so the difference with this approach, so the policyholder is benefited from the profit of his or equity. So here I would say that I would say that there is a general, so the PD that we derive, of course, depends on the model for financial and actual risk. If there are different guarantees in case of death and survival, in fact, the PD is the same, because here for the PD, we consider a general function D for the death benefit and a general function S for the survival benefit. So if the benefits are different for the policyholder, the approach is exactly the same. Now, the point is, if it changes the dynamic of the hedging portfolio, that would also affect the dynamic of the PD at the end. Now, it depends on exactly what is this type of contract, but if there is just a change of fees or this type of things, I would say that the approach doesn't change. We just need to change the appropriate parameters.
Okay, great. So we have Mr. or Mrs. Chalak. If you can write your question, that would be better. Let's see, something has shown up.
There is
yes.
Bayan Wisi.
Yes, Bayan Wisi. Yeah. Thank you for your attractive talk. I have two questions. One, is it necessary to compare this price with price of real markets? and your goal is just to find price, and the number of hedging strategies do not deter that are not determined. I think she's referring to the fact that if you have already applied it to real data, when well, this is just simulation, I think, right?
Yeah. So in fact, the input that I need are in fact the parameters for the equity and so on. So these so I need the different parameters. So I just took some initial parameters from previous studies, and given these parameters, I determined what was the price surface. Yeah. So I did not compare with price of real markets, but also the thing is that it's not like I can compare with the thing is that here we price equity linked life insurance. So I would say there is no market for equity linked. It's not like I can go on a website and find some price of equity link, or at least I don't think it's available. You can find a price of options, but so yeah, that would be hard to compare our fair value with some real, price proposed by insurer, because I don't think it's available. And then that's for, and then the second question, your goal is to find the price. And yeah, so the good thing with our approach is that we determine the price, but also in fact the hedging strategy, because in fact the neural networks also determine the θ1 and θ2 that I mentioned. So it means that with this approach, given some market conditions, the neural network can tell you how should you invest in bonds and equity. So that's quite powerful, because it gives you like the hedging strategy for any market conditions.
Okay, great. And what if you add a jump to your equity process? Does that make a huge change?
Let me think. I would say we can consider the of course it will change the final PDE, because in the PDE, in fact, there are two parts in the risk margin. There is one part which is related to the diffusion parts, and there is one part which is related to the jump of the insurance process. So I guess that if the stock is a jump diffusion process, there should be also I guess a risk margin for the jump component of the stock itself. So so it means that because in fact all these risk margin are due to risk that you cannot hedge. In fact, if you go from a Black-Scholes market to a jump diffusion market like a Merton model, you already go to an incomplete market. So there is also already a risk margin for this jump part. So I would say that we have to redo the calculations, because I do to derive the PDE, I just did the computation by hand. So if we change the dynamic of the process, we have to redo to derive the new PDE. But I would guess that the general approach does not change, but the risk margin will have probably a third term in addition.
Okay, great. A follow-up question from Bayan. Thanks for your answer. Another question: in which situation we can have a complete market? It's very difficult to have, actually.
Well, I would say in insurance, in insurance, I would say it's almost impossible to find a complete market, in the sense that a complete market would mean that you can replicate all your insurance liabilities with product with financial products, and well, because the mortality risk cannot be I mean, because in fact, the main problem in insurance is that you don't have a market for mortality. I would say that if in the future there is a market for the mortality risk, maybe if you add then this, let us say that, for instance, in fact, you can come to a close, let us say that you have bonds and equity. And let us say that you have, for instance, longevity bonds, which are like bonds on the longevity. In fact, when you include the longevity bonds, you are in some sense completing the market. So you are closer to a complete market. So the more financial products are based on mortality and longevity, the closer you are to a complete market. The thing is that at the moment, the longevity market is still a small market, so not really liquid. But maybe we can hope that in the future the market will be more liquid, and then you will be more able to hedge your insurance liabilities.
Yes, that is also a really interesting question in relation to Iran, because we had a panel discussing the ILS, insurance-linked securities, and this is exactly that if you want to introduce a security, this is still an issue in Iran, and I would say all around the world, it's not very obvious to introduce insurance-linked securities. In Iran, we had the problem that the rates offered by the insurance body and the financial body are totally different. And that is why the financial body is still not convinced that this type of products are worth investing, right? So for that reason, it hasn't gone ahead. We are hoping that one day we can have these products in Iran, but as Karim also said, it's not a huge market, as liquid as the equity market or other type of market. So that is why it's at the moment really difficult to discuss whether we can have like longevity bonds at disposal to find them very liquid and make the market complete. So that is why we have to deal with incomplete market. That's no choice for us at the moment. And the model that Karim is setting up is totally an incomplete market. So that's a good approach to this type of problems. Okay, Karim, thank you very much.
Thank you very much.
Yes, that was a wonderful talk. You are a very good speaker. I have to say that. Yes. Okay.